we might be able to get to the point of answering that question there about that little device in that plane, hopefully. But first, let's go back to our example applications of the principles that we've introduced of conservation of mass and momentum and Bernoulli's equation. And this is the fourth type of problems. First was jets, including thrust of a rocket. Second was nozzles. Third was, what was it we just did? Vanes. And fourth is pipe bends. And this is, again, a very important application for engineering design questions, because we have to normally be able to dimension the supports of these systems. So the tips for this situation are to assume constant velocity across the pipe, which, like Nathan said before, we just assume a constant velocity to simplify our life and use an average velocity. And the difference with vanes is that in this case pressure forces play a role. So let's look at the numerical example immediately, which is corresponds to this sketch over here, where we have a 1 meter diameter pipe with this horizontal bend. So what I mean by horizontal is we're actually looking at the pipe from the top, right? So it's in the horizontal plane, it's bending, okay? It bends on a 30-degree angle. It's carrying crude oil, which has a specific gravity of 0.94. And we have a steady flow rate of 2 cubic meters per second and a bend of 30 degrees. Of course, the question is the force to hold the bend in place. But we're giving a little bit more here to simplify things in this picture here. And these additional pieces of information are going to be useful. One is the volume of oil in the whole piece of pipe here in the bend. And that is equal to 1.2 cubic meters. So the volume in this whole piece here. The empty weight of the bend is equal to 4 kilonewton. These things are normally quite large, and so we have to consider now, there's a big piece of pipe. Yes? Yes, correct. We want to find, there's a constant pressure in the bend as well. Inside the pipe. And it's 75 kilopascal gauge. And of course the question is the force to hold the bend in place. Our first trick is to choose our control volume wisely, and the way we choose a control volume similarly to the veins problem is we want to make sure that the velocity is perpendicular to the control surfaces so that we can very easily calculate the fluxes. So in this picture here, I'm going to draw a control volume that is crossing right like in the nozzle problem, perpendicular to the pipe at the flanges. In this area I don't really care much what the shape is because I'm not going to use that surface, but it is perpendicular to the force in the areas that cross the pipe. So we have a reaction that I'm going to draw as an average reaction for the whole bend in two components, Rx and Ry. That's going to be the reactions that we need to find. Free body diagram, so far so good, but in this case we also have to consider the pressure. The whole thing is not an atmospheric pressure like the vein where the jet is a free jet, but actually there's a fluid inside a pipe here at a certain pressure. So we have pressure times area. In this phase here we have P times A, and in this one here we also have P times A. We have pressure forces across the control surfaces. Yes? It's a top view. The weight is pointing, say, across in the opposite direction here. Yes, down the. Let me see, how did I draw my axis correctly? If that's X and that's Y, I think Z has to be upwards here, that right? So the weight is going down there. I don't know how to draw that in perspective, but the weight is into the page. Okay? Yeah, it's a horizontal bend and I'm looking from the top. Yeah, so what am I doing in terms of my axis? I've drawn X, Y, and Z has to come up there in my picture. Yes? To be correct. So we've got all the forces now. Now let's add our momentum fluxes as well. We have m dot v in both, like in the vein, m dot v, that's it. Let me just make a little space for m dot v here that you can read it. And m dot v out. So we have pressure forces and reaction forces at the flanges, and we have flux of momentum in and out, plus the weight which we need to consider eventually for the resultant, but it's not going to be affected by the momentum fluxes because they happen in different directions. So in the vector form of the momentum equation, sum of forces is equal to, this is a steady situation, so the derivative with respect to time doesn't appear, that term is zero, and we only have the fluxes of momentum. So sum of m dot v out minus sum of m dot v in. Steady, it's a steady case. The forces are the weight of the pipe and the oil inside, which goes in the negative z direction, plus the reactions that we've drawn in the x and y direction, and the forces, and the pressure forces. Those are all the forces we have. Yes?
Why don't we put reactions on other?
We do, but we've just taken them all together and bunched them into just one reaction. And we don't worry about those details now. We just have the total final net force on the control volume. Once we find that, then we could, if we want to design the devices mechanically, we can take into consideration how that force is going to be distributed. So we're looking at the net force now. Yes? We're going to consider the weight because we're going to end up with a vector force to hold the bend in place, which has a total magnitude, which is the sum of the three components, x, y, and z. And those are all going to be of importance in the design problem that must follow, right? But the z direction does not interact with the momentum balance that we're going to do. It's just it's going to be an additional component that we must not forget. So, of course, there is a reaction, is what I'm saying. There is a reaction in the z direction, which is equal and opposite the weight. Because this thing is not moving, so it has to be. There's three components to the reaction. The r and y direction interact with pressure and exchange of momentum, and the z component of the reaction simply is opposite the weight. That's what we're going to find. So we can actually pretty much write all the forces now. The sum of forces is, again, the weight of the pipe plus oil inside, which points in the negative z direction, and all the pressures and the reactions. And so we have sum of forces as a vector is equal to, let's look at the x direction first. The x direction we've drawn the reaction in the positive x direction, so plus Rx, with P times A is also pointing in the same direction, plus PA, pressure times area. And we have a component of pressure here also. Yes, I've drawn the pressure wrong in my picture, okay? Because the pressure, we always draw pressure as acting normal to any surface, right? So the pressure couldn't be pulling. Pressure is always pushing, correct? So I've actually drawn the arrow here in a way that is not entirely correct for the purposes of considering fluid pressure. Fluid pressure always acts perpendicular to every surface. So forgive me for that confusion. And now it makes sense that I would have minus P times A times the, so I have cosine of theta. Let me see if that makes sense. Okay, yes. And all of that in the y direction. In the I hat direction, which is the unit vector for the x coordinate. So that's the x direction. I'm doing this in vector form. So now let's go to the other component. In the y direction we have Ry. The pressure on this side doesn't have any component, but the pressure on the other side does, and it's in the positive y direction. So P A sine theta, and all of this time my unit vector J. And finally we have a reaction in the z direction which I've not drawn but has to be equal and opposite the weight because this whole thing is in balance. So this is our vector force. Make sense? Answer your question? Yes? Can you repeat your question? The pressure, we always consider the pressure to push on surfaces, basically. So on any surface here, the pressure that the fluid is applying on this control, basically is the fluid on the other side of the pipe, right? The fluid on the other side of the pipe that I've cut out of my picture when I drew this box, which is my control volume, is pushing on that area. It's not pulling. It couldn't possibly do that. Always pressure acts normal to every surface. That's I just sort of mechanically drew the arrow in the wrong direction because the momentum does point that way, but it was a mistake. You could have negative pressure gauge, but not absolute, and see all of this thing is inside a pipe. So, yes?
Why didn't we consider forces in the
In the problem, we weren't given the weight, and it's probably going to be negligible with respect to how veins work, is you have a really strong jet that is hitting on that vein, and if you were, first of all, the fluid is not confined. The fluid is a free jet, so we don't need to consider that. We could have wanted to consider the weight of the vein itself, right? But normally it's just a little small device that is receiving a big jet. It's in the context of that problem, it was considered negligible, and you were not even given the information in the problem setup because of that. In this case, you're given. The problem setup is quite different. We have a big steel pipe with crude oil inside. This thing is heavy. Yeah, it's a very different situation, and it's not moving that fast. So it's just it's a different engineering situation altogether. Yes.
So kind of like a rule of thumb, would you just put the forces due to fluid pressure, the normal endpoint anywhere to the control volume?
Yes. 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 Always. So to repeat that, what he said is forces due to pressure always are pointing inwards, normal and inwards to every controlled surface. Always pushing on every controlled surface, yes.
Would it be wrong to put the second pressure force pattern, like inside along the momentum?
Inside?
Like inside the control volume?
Remember, we don't care anything that happens inside the control volume. The inside of the control volume is a black box. That's the whole purpose of this type of analysis. We draw a black box. Everything that happens inside is some sort of average out that we don't care. But we're looking at the control volume from outside and want to find out how the control volume interacts with the world. So for that reason, the pressure is going to be always, the pressure in this case is the pressure exerted by the oil in the piece of pipe that we've cut out. And it's always going to be pushing into the control surface. That way. Yeah. Okay, so we've drawn all our forces, and we've got all of the components there. And now we need to look at the momentum flux. And the momentum flux, remember this part is easy, right? The reaction in the z direction is immediately known, but the other reactions are not immediately known. So for those we do the momentum outflow and inflow. The sum of momentum going out is momentum going out. We have two components. So basically, we can separate it in vector form. We're going to write it as m dot v times cosine of theta in the x direction minus the momentum is going in the minus y direction, m dot v sine theta j, and sum of momentum in is only in the positive x direction. So now we can do force balance component-wise. And we have, say, the x direction. We have Rx plus PA minus PA cosine theta. That's the forces in the x direction. And that has to be equal to momentum out minus momentum in. So m dot v cosine theta minus m dot v. In the y direction, it's a little bit easier. We have Ry plus PA sine theta equal to m dot v. Oh no, what is the sine theta? Is j, same, yes, sine theta. Minus, yes, thank you. Thank you, yes, minus sine. And Rz equals weight. So far so good. So let's put some numbers in here to see that this all works out and that we can calculate everything. Let's go a little bit further. So how do I do that? I'm going to have to just clear the slide. And these equations here, you've all written them down, so we'll continue from there. Note that PA appears in the same 4 everywhere, so I'm going to, that term I can calculate. And so PA, the pressure was given, and the area, we're given the diameter of the pipe, so we can calculate that. The pressure is 75 kilopascal, and yeah, so that kilopascal is kilonewton per square meter, so remember that we make sure that we've got all of the units correctly. And we have pi r square points. There was a 1 meter diameter, so I'm just taking half to use the radius here, 0.5 meters squared. And that is, so meter squared, and this is kilonewton divided by meter squared. So this is going to give me kilonewton in the end when I multiply these numbers. 58.9 kilonewton. Okay. The fluid speed was not given, but we were given the volume flow rate. So to get the speed, we must use the volume flow rate. So remember, volume flow rate is V times A. This is what's given. And it was 2 cubic meters per second. That's the information that was given, volume flow rate. So we need to get V as Q divided by A, or 2 cubic meters per second divided by, and the area is pi 0.5 meters squared. And as it should, I obtain meters per second in my units. And the number, if I put those in the calculator, 2.55 meters per second. So now I can obtain the momentum flux term that appears, which is always m dot v. M dot v appears many times in our previous expressions, and that is, well, the easiest way that we can do this is to use the volume flow rate and multiply by the density, and that's going to give me the mass flow rate. So basically I want to do rho Q times V. And rho, we're giving the specific gravity, so I multiply the specific gravity 0.94 times the density of water, 1,000 kilograms per cubic meter. So that's rho of the oil. Q was given 2.0 meters cubed divided by second, and the velocity I've just calculated, 2.55 meters per second. So you see this meter cube cancels out, and I have kilogram per meter divided by second square, which is the correct unit that I should have. Units of force, basically. This is equal to 4.79 kilonewton. And now we have all the terms that I could plug in to get my reactions, Rx, Ry, and Rz. And I'm just going to give you the answer, and you should review this later in your own time. Remember, we had for Rx, we just had the terms P times A, which is we've calculated here, M dot V, which we've calculated here, and the angle. Those were the only types of terms that we had in the expression. So now we can plug all of that in and obtain it. I get Rx equals to minus 8.53 kilonewton, Ry equal to minus 31.8 kilonewton. So the forces point in the opposite direction than we drew them on the free body diagram. And Rz equal to 15.1 kilonewton, basically just the weight, which is the weight of the pipe was given, and the volume of the fluid inside was given, multiplied by the density, and we obtained the weight. So this is all that we do here. So is all that procedure clear? This is another of the typical applications that you may have. We've seen 4 typical applications with one example for each one of them. And of course, you'll do some more problems of that same type in your homework. Now I want to go back a little bit to Bernoulli's equation. Okay? Let's go back to Bernoulli's equation. I've written it here the way we've presented it again, and I've listed here again the assumptions. We have assumed that the flow is steady, so all derivatives with respect to time are always equal to 0. In this, we've assumed constant density, rho equals to a constant. We have assumed no shear stresses, so the flow is inviscid. Viscosity is equal to 0. We assume no heat transfer and no work, and single inlet, single outlet. Those are the assumptions for the form of the Bernoulli equation that we presented so far. Now, we can interpret the last condition here, single inlet, single outlet, in the limit for what we call a stream tube, or even further in the limit to a streamline. Now there is a more rigorous way to derive the Bernoulli equation by applying Newton's second law following a streamline. We're not going to do it in class, but I'm going to provide for those of you who are interested and get pleasure from mathematics, the full derivation there in an additional sort of supplementary theory video. But I realize that some of you have that inclination, more mathematical inclination, and many of you do not, and so it's just an optional, just for your enjoyment. If you're so inclined, I will provide that. But we won't do the full proof in class. So you can see here, just in physical intuition, that it makes sense that if I consider a pipe, I could also consider a little the limit of a very, very thin, sort of hair-thin streamline or stream tube. So let's define a streamline to make sure that we understand what it means. A streamline, the definition of a streamline is a curve that is always tangent to the velocity. The velocity vector. So if I were to consider, for example, the flow around an airfoil, and I consider the fluid approaching and moving around the airfoil, then at every point in space I could draw a line that is always tangent to the velocity vector. And that would be the streamline. Now a stream tube, which is drawn here in this cartoon, is formed by a set of streamlines starting at points that form a closed loop, as in this cartoon. Each one of these blue lines in the cartoon, or the dashed lines that are in the back of this sort of element of fluid that has this tube shape, each one of those lines is a streamline. Because each one of these lines is a streamline, the velocity vector is always tangent to that line. And therefore there is no flux at all of fluid across that surface. There's only flux going in this area and out the other one. So it's like a tube. We call it a stream tube. Like a tube or a pipe, but there's no flow across. This is like it was a pipe around it. It doesn't make any difference. There is no pipe, but the fluid behaves the same way. And therefore I can interpret that in the way that we have for the Bernoulli equation, where we have a single inlet and a single outlet. This is the concept that we want to utilize for applying Bernoulli equation in these situations. We look at a small tube of fluid where the fluid enters on one end and comes out the other end, but it cannot go through any of those walls because they're formed by a streamline. Does that make sense, everyone? Can you follow that? Okay, good. So then we can write another form of the Bernoulli equation for this situation, and for this situation then we write, I'm going to write here, Bernoulli equation for that case, P plus 1/2 rho v squared plus gamma z, I've written rho g as gamma, equals to a constant along, well, either this very, I'm going to now make that stream to infinitely thin, and it's going to be along the streamline. And this is going to be another form of the Bernoulli equation that we're going to find quite useful. Is that clear? Okay, good. Now you're going to have to use the Bernoulli equation for your lab that you're going to start this week, and so I want to make sure that everybody has seen this, although it's also explained in your lab manual. We want to discuss it in class as well. So this is another form of the Bernoulli equation, and we are going to then write, did I have a, oh, okay. So this is the other form of the Bernoulli equation. I'm going to write it again, P plus 1/2 rho v squared plus gamma z equals to constant along a streamline. And I want to note that there are three processes involved. We have pressure, P. We have weight, which is in that term gamma z. And we have mass times acceleration. In that term that is 1/2 rho v squared. So there's an interpretation that we can make, sort of physical insight that we can gain from looking at it this way. The interpretation is that Bernoulli's equation tells us that the work done by pressure on a fluid particle and weight is equal to the change in kinetic energy, which is represented in this term here. This is our interpretation. We interpret it as the work done by pressure and weight forces is equal to the change in kinetic energy of a fluid particle. Okay? That's our interpretation of that form of the Bernoulli equation. Now, an alternative form, again, would be obtained if I divide over that equation by gamma. And in that case, I'm going to, this is an alternative form, and it's going to be P over gamma plus V squared divided by rho g, 2g, the rho cancels out, plus z equals to constant along a streamline. Now notice that by dividing over by gamma, the equation now has the dimensions of length. You can see that clearly from this term. Now you recall that we said that when we're measuring pressure, we can use a measure of, in terms of length, which is the length, the height of a column of fluid that generates the same pressure that we're measuring. And this is a similar situation. We have pressure here, but it's in units of length. And so this is basically a tradition of civil engineering to look at these sort of energies in terms of a units of length. In terms of unit of length, when we have units of length and we're measuring pressures and so on, it's what we call the heads, if you recall the pressure head. So this term is called, from just tradition of civil engineering, the pressure head. This one is the velocity head. And Z is the elevation head. And in this form, it is used very often for things like, perhaps a pipe that comes down a hill, and we want to calculate the velocity at the bottom, and so on. We're going to use it in these sorts of forms. So the pressure head is related to the height of a column of fluid that produces the pressure P. The velocity head is basically could be like the distance in free fall to reach a velocity v. And the elevation head is related to potential energy. It's another way to interpret this. And the sum of all of these must be a constant. So this is like an energy interpretation of this. We're going to use the Bernoulli equation now in several contexts. The first one is for measuring pressure. So we're going to interpret each term of the Bernoulli equation as a form of pressure. And we're going to define these different forms of pressure: static pressure, stagnation pressure, dynamic pressure, and total pressures. And these come from interpreting each term in the Bernoulli equation as a pressure. So I think I have, okay, later on. So, how do we interpret each term in terms of pressure? So P, we're going to call the static pressure. Basically, this is just the pressure from thermodynamics. This term rho 1/2 rho v squared is going to be interpreted as the dynamic pressure. Gamma z is like a hydrostatic pressure. So gamma z is hydrostatic. And so let's see this in a more physical situation. Let's consider this case here. So we have a fluid coming inside a pipe, and we have some piezometer. We've discussed before the ways of measuring pressure. So the piezometer here would measure, right, a piezometer would measure the excuse me, pressure at 1, the point 1 here, by the column of liquid that we would see in this tube, right? So how do we do this with the manometer in the manometer problem? If you recall the manometer problem, same fluid, same elevation is same pressure, but here we're changing elevation if we go from 1 to 4. And so from 1 to 3, pressure at 1 is equal to the pressure at 3 plus gamma times the H between 1 and 3. I called it H31 here. Then pressure here is the atmospheric pressure, so pressure at 4 is atmospheric, and so pressure at 3 is equal to P4, which is 0 gauge, times gamma H41, 43, yeah, sorry, 43. 43, this is this guy over here, 43. The notation is they're using the points. And so the total H here is between 1 and 4 is H31 plus H43. That's the total H drawn here. And so we use that height of fluid to determine the pressure at 1, like we did with the manometer problems. P1 is simply gamma H. So you see this pressure at P1, the pressure of the fluid, P, in the Bernoulli equation, is the same pressure as would be measured by any piezometer at that point, at that section of pipe. So the pressure measured by a piezometer is a static pressure, the actual thermodynamic pressure of the fluid there. Now, if I look at this other point here, point 2, just a couple more minutes, and we'll continue next class with applying Bernoulli's equation, but let me just point out that the pressure at point 2, we have a pressure, the fluid goes in there, and what we have here is like a small little tube that is bent, and so the fluid goes in, and it has to come to a full stop because the fluid inside this little pipe is actually static. So at 2 we have that the velocity at 2 is equal to 0. Velocity inside the little tube is 0. And this, so the pressure, and for this reason, the pressure measured at 2 is called the stagnation pressure. So the fluid becomes stagnant. It enters that little pipe and it stops in its tracks to 0. And that generates a different column, height of the column of liquid there, if we were to build a piezometer here that turns and faces the flow. Basically, the flow pushes the column of fluid a little bit higher than it would be if we were just measuring static pressure here. So this is, the point 2 is also called the stagnation point. And so now all we need to do is Bernoulli's equation between 1 and 2. And I note that between 1 and 2, the fluid, this is a streamline. Everywhere perpendicular to the velocity. So I can apply this new way of looking at the Bernoulli equation in a very, very thin little tube, which is actually in the limit a streamline. And I apply Bernoulli's equation here, and I have P2 plus 1. The elevation is the same, so I'm just going to have 1/2 rho V squared, B2 squared, which is 0 actually. This is 0, equal to P1 plus 1/2 rho V1 squared. So we note that the pressure at point 2 is larger than the pressure at point 1. And this pressure is the stagnation pressure, P2. Stagnation pressure happens in the fluid whenever the fluid comes to a complete stop. And it happens in any situation of a submerged body, for example, flow around an airfoil, flow around any object. There will always be a point where the fluid comes to a complete stop, and that's a streamline. That is the stagnation streamline, and that allows us to measure this stagnation pressure. So we'll continue from this point on next class.